Okay, this is the third video on Radians, and actually it will be the last of the sort of content videos. It's not a long chapter by any means, but it does take some time to master, so it's the majority of your time is going to be spent practicing rather than watching. So what have we got? We've got the formula for the area of a sector of a circle is also simpler when you use radians. And to find the area, you use the formula the area equals a half r squared theta. R is the radius, theta is that angle again that's inside the sector. So let's have a look. Now again, I'm going to do this slightly differently. We're going to use if it was theta in degrees, it would be theta over 360 times pi r squared. That would give us the area of a sector. We're not working in degrees, that would be for deg. So if we're working with radians, we know that that's theta over 2 pi times pi r squared. And so this is for rad. Now what actually happens here is, that's one of the things that doesn't go. Let's just, let's go back. Pi r squared, that's in radians. So what have we got? Well, the pi's cancel this time. And we just write it slightly differently to what you can see there. We write it as a half, which is obviously the 2 on the bottom, times theta times r squared, but we rearrange that to a half r squared theta. Okay, so the area in radians, if we've got an angle in radians, is given as a half r squared theta, and you'll be using that a lot. In fact, we're going to use that now in example 8. It says the area of minor sector AOB, and by minor sector it means this smaller one, as opposed to the major sector, which would be, unsurprisingly, the bigger one. Okay, but we're dealing with the little one. Minor sector AOB is 28.9. Given that angle AOB is 0.8, calculate the value of r. So start with, let's just write down what we've got. We've got area equals a half r squared theta, and now it's a substitutional exercise, isn't it? We've got 28.9 is the area, equals a half r squared, which we don't yet know, times by 0.8, and we can solve however we want from there. Double both sides and then divide, or we could do a half times 0.8, which is 0.4, and divide by that. So let's do that. So we've got 28.9 over 0.4 equals r squared, and that tells us that r squared equals 72.25. So r is the square root of that, which of course is 8.5 centimetres. Obviously there are two solutions, but we are dealing in lengths, and a length struggles to be negative. Okay, so we've got 8.5 centimetres. Then moving on, we've got example 9, and what have we got here? I've got a plot of land in the shape of a sector of a circle of radius 55 metres. The length of fencing that is erected along the edge of the plot to enclose the land is 176 metres. Calculate the area of the plot of land. Well, let's first of all just draw ourselves a quick diagram. So there's our two radii. I'm not sure that second one is particularly close in length. Let's try and just get that a bit more accurate. And here we go again. Let's see if we can make this look like the arc of a circle. It's average, very average. Now, what have we got? The radius is 55, so that's 55, as is this one in length. We haven't got anything else particularly, but what we will do is mark in that this is theta in the angle in the middle, and this we will call, let's just call it L. So the perimeter equals 2 times the radius plus L. So that is 110 plus 55 theta. That's because, of course, the 110 is the 55 and the 55. And the 55 theta part is L. r theta to give us that curve length. Now we know the perimeter is 176, so from there we can work out fairly quickly that that gives us 176 minus 110 will be 66. So we've got 66 equals 55 theta. So theta is 66 over 55, which both are divisible by, well, we don't need to cancel, we can just work it out to get 1.2 radians. Okay, so we've got our theta, but it doesn't want that, it wants the area of the plot of land. So the area is a half times 55 squared, half r squared times theta, which we can pop in our calculator, and we get 1,815 meters squared, and there's our solution. Okay, so that's up to example 9. In the next video, yeah, I'm going to do it in another video, we will move on to the segment area. In fact, let's do it in this one. Let's just carry on. So you can work out the area of a segment using radians, and a segment is like this section here, this section A, and this would be the minor segment, and the major segment is the other side of the chord. Okay, so a chord across the circle makes 2 segments rather than what we've been working with, which of course are sectors, not to be confused. So, example 10, show that the area of, well, firstly you're given the formula, the area of a segment in a circle of a radius r is this. Okay, so we've got the area is a half r squared theta minus sine theta. That will give us the area of A here when we know the radius and we know the angle at the centre. Now, where does it come from? Well, firstly, let's go back to the right colour. And what we do is we work out, firstly, actually, we'll do it in a nice colour. We're going to work out the area of this sector, okay, that sector, and once we've worked that out, we'll then take away the area of the triangle, which we can calculate, and then we'll be left with the area of the segment. Okay, that's the principle, and it is relatively straightforward. So we'll start with, what did we say? We said we're going to find the area of the sector, and the sector is pretty easy. That is simply a half r squared theta. No problems. Now the triangle, if we, let's maybe do it slightly neater than that. Shouldn't be lazy. Triangle, we can sort of try and roughly make it look a similar sort of shape. And that is theta. We've got R and R. So actually we've got plenty of information there. We've got the angle in between the 2 radii. So that's, if we think about the area of the triangle, we can work that out. Area of a triangle is a half AB sine C, which we know from chapter 2. But we're not dealing with A, B's and C's, so we can use, just to point out, of course, if you're using a half AB sine C, A and B are the 2 sides that surround the angle C. Okay, so using that, we've got the area of our triangle is a half. A and B are both R, because it's an isosceles triangle, because they're both the radius, times the sine of theta. Okay, so if we then want to work out, let's just scroll down, area of segment will be the area of the sector minus the area of the triangle, and we will be there, a half r squared theta minus a half r squared sine theta. Now that's not the same as theirs. Theirs has a slightly different look to it, and to get that we are going to take a factor of a half and r squared out of both. So a half r squared, and then we would times that by theta to get this first part, and then we need to minus sine theta to get this second part. And we are left with the area of a segment, a minor segment, okay? Or a major segment, actually. Now, example 11. In the diagram, AB is the diameter of a circle of radius r, BOC is theta radians. Given that the area of triangle AOC is 3 times that of the shaded segment, show that this is the case. So, it's again just a case of sort of breaking it down bit by bit. And what we have is, just give me one sec, AOC. Okay, so triangle AOC, let's start with that. Triangle AOC equals, in area, and I'm just going to talk about area. Area is, well, firstly, let's just look at this. This angle here is going to be pi minus theta. I think you'd agree. Pi minus theta in radians. So the area will be a half r squared, and that's the radius as well in there, of course, because it's a radius of the circle. That's r as well. So it'll be a half r squared sine, and then our angle, which is pi minus theta. So this is triangle AOC here. Okay, so we started off with AOC, and we found the area would be a half r squared sine pi minus theta. Now, this is quite critical. Actually, if you think in terms of your degrees, pi minus theta, if you do sine of pi minus theta, if we go back to degrees, that's like sine of 180 minus theta. Well, 180 sine of 180 minus theta is actually equal to sine theta. And you can think of that in many different ways. If I was to very quickly do this, then it would be a dreadful sine curve. But if we were to pick an angle, say here, and an angle, say here, they should both give us exactly the same value. And as this is 180 minus theta would be the same as theta itself. If that's not making any sense, do ask me, but I'm not going to go through it on here. I will happily go through it with individuals, so do let me know if that's something you're not sure about. But ultimately, we can say that the area of triangle AOC is a half r squared sine theta. Okay, so that is the area of AOC. Now, we also can work out the area of the segment. And the area of the segment, and we can just use our formula, will be a half r squared brackets theta minus sine theta. We've just looked at that. So what do we now have? Well, the information we're given is that AOC, triangle AOC, is 3 times that of the shaded segment. So if I multiply the shaded segment by 3, that equals the area of the triangle. So triangle is a half r squared sine theta, and that is equal to 3 times the segment. So that's 3 times a half r squared brackets theta minus sine theta. Okay, we've got an equation formed, and you can bet your bottom dollar if we rearrange this equation properly, we should be able to end up with this 3 theta minus 4 sine theta equals 0. So let's have a look and see if we can do that without any mistakes. Well, the first thing we can do is divide both sides by a half r squared. If we do that, they disappear, and that makes life a bit easier to begin with. So we're left with sine theta equals 3 lots of theta minus sine theta. Then if we expand the bracket, we get sine theta equals 3 theta minus 3 sine theta, and then minus sine, which side do they take it to? Yeah, they take it to the right, so we'll minus sine theta from both sides, and we get 3 theta minus 4 sine theta. And that's exactly what they wanted. Okay? So we're done. What does this really tell us? Well, at the moment, that's not a massive issue. What we have managed to do is show what they wanted us to show. And we've shown that 3 theta minus 4 sine theta equals 0. It may well be of use, and it's possible that in possibly C2, but more likely C3 and C4, you'll use something like this to then go on and solve a more tricky problem. But that's it. That's where we are. I'm just having a look now. The next part of this process is working through exercise 6C. I know this has been a long video, but we've covered quite a lot in 6C. We started off, of course, with just the area of a sector, and then we moved on to the area of a segment. So don't forget that when you're doing 6C. First of all, start with the easy parts. Once you've done the easier questions on just the area of the sectors, you then move on and start thinking about some of the segment work. And it's a bit of a monster exercise. And after that, you're then straight into the mixed exercise. And in the nearest future, I'll put up some worked solutions from the mixed exercise and any other questions you're not sure about, if you let me know. But that's it. That is pretty much everything you need to know about radians for C2. It's now a case of going away and practicing it and working through each of the questions, working through the mixed exercise, and you'll be fine with it. I wish you every success. And if you've got any problems, of course, you know you can get in touch with me either by emailing me or seeing me at school. And of course, I'm happy to help either way. All the best and good luck.